Now to this point, we've talked about factor analysis and showed how many factors we can derive from a data set. What we need to talk about next is how factor loadings are obtained from the correlation matrix. So I've entitled this Calculating Factor Loadings because that's what we are going to do today. It is important that you refer to videos 3.38 and 3.40 on eigenvalues and eigenvectors, and as well as normalized vectors or normalization, since factor loadings are nothing more than eigenvectors normalized to their eigenvalues. Now, as we talked about there in chapter 3, there's a certain class of matrices, which includes correlation matrices, which we're going to deal with today. For that class of matrices, there exists a certain vectors x, such that when the matrix is post-multiplied by them, the resultant vector is equal to vector x times a constant, which we call lambda. And it can be shown here. You can imagine changing this to, this is the formula that we had in chapter 3. A is either a correlation matrix, covariance matrix, SSCP matrix, and you post-multiply that by a vector x. And when you do that, that vector will produce x times a constant lambda. Where, if you recall, the vector x is an eigenvector of matrix A, and lambda is the eigenvalue corresponding to that eigenvector. Now, when the correlation matrix R from the data we've been dealing with from the Locurto et al. 2006 data is post-multiplied by F1, or F, which is just the factor loadings on factor 1, we can have a similar formula. So we can replace A with our correlation matrix R, and replace the x vector with F, which is once again our factor loadings. And we can get a resultant vector that is equal to the factor loadings times a constant, and we will see that this constant lambda is 1.414. Now, you might want to refer back to table 4.3 and look at factor 1. Factor 1 in the table says 0.40, factor 2 0.31, 0.81, negative 0.71, and then the last task 0.06. But those were rounded, and these are the values that we actually have. So when we do matrix multiplication to get our correlation matrix times the factor loadings there, this is the resultant matrix. Now this is equal to the factor loadings times this constant lambda, and I'll show you that here. Okay, there may be some rounding error, but you see that it's essentially the same. Now, a more basic form of the equation uses k. And the equation I have put right here, rk equals k lambda. So the more basic form of this equation uses k, which is the eigenvector normalized to 1 rather than using f. And once again, in chapter 3, we talked about normalization, but just for a quick review, a vector is normalized to 1 by dividing by its magnitude, which is the square root of its sum of squares. In other words, it is divided by the square root of the value to which it's currently normalized. In this case, it's normalized to lambda. So our equation here, if you look here in the center on the left, our equation is k equals f over the square root of lambda, or a factor loading matrix over the square root of lambda, which is the factor loading over the square root of 1.414. So I'm going to demonstrate that here. We're going to do equals, and I'll put this in parentheses, our factor loadings, so f, that's going to be divided by square root of 1.414. And those are the values that we get. And you can see that I went ahead and put them down here in their respective positions. So this is basically the same equation as before, except now it's normalized. The eigenvector is normalized to 1. So we can do matrix multiplication here and take our correlation matrix, and then our the eigenvector normalized to 1, which is k, and we'll get that, and we see that r times k is the same thing as k times lambda, lambda still being 1.414. Okay. So essentially the same, like I said, a little bit of rounding error, but essentially the same. So I want to know, as does your text here, as explained in chapter 3, and as we just demonstrated, eigenvectors have an interesting property of reproducing themselves, but multiplied by a constant, when a correlation matrix is post-multiplied by them. So eigen means self, if that helps you remember. So eigenvectors, once again, reproduce themselves. So we see that here when we post-multiply an eigenvector, or a correlation matrix being post-multiplied by this eigenvector, we get the eigenvector again multiplied by a constant. Now let's get into the deep and dirty stuff of it. How is the eigenvector actually obtained from the correlation matrix? Like I said before, this eigenvector was this factor loadings that we had on table, I believe it was table 4.3 in the text. But how did we actually get it? The simplest way to state it is to say that we first raise the correlation matrix R to a particular power, reasonably high. The eigenvector is then found as the vector of row sums of this R matrix that has been raised to a particular power. And I will show you how this is done. Moving over here, you see that I put our correlation matrix R. Now looking at this screen, you can see that I'm going to do R squared, R to the 4th power, R to the 8th, R to the 16th, but I'm actually going to use R to the 32nd, and I'll show you how that's done. So just think about that and consider two matrices. We've got R, our correlation matrix, and R to the 32nd power. That matrix is created by squaring R, or multiplying it by itself. Using you can use matrix multiplication, and then squaring its square and continuing that 5 times. So for each successive matrix power, we will get we will create a vector of row sums, which I will say is M, be symbolized as M. So M1 for the R matrix, and M32 for R to the 32nd power matrix. And this is done by post-multiplying each successive matrix of R to some power by a vector of 1s. So if we want to get the row sums, we just create a vector of 1s. And we'll do matrix multiplication to get the row sums here. So we see it as the values of 1, 0.73, 1.1, 0.5, and 1.05. So now I'm going to create R squared, R to the 4th, and continue until I get R to the 32nd. So what I'm going to do for r squared, I'm going to highlight a 5 by 5 matrix. Make that equal to, we're going to do matrix multiplication. We're going to do r times r. Okay, then do the same thing. Matrix multiplication, r squared, same one again. And I'm going to repeat this. Five times. So this is the fourth time we're going to do r to the 8th. So r to the 8th. And then one last time. And I'm putting these out here just so you can see the successive order that I do it in. Okay, so these are the values that we have for our matrix r to the 32nd. Now we want row sums of these, so we're going to do ones. And let's do matrix multiplication again to get the row sums. And these are the values that you get. And once again, what I mean by row sums, denoted by m here, is where if you look, it's easier on m1 here. If you add these together, 1 minus 0.21 plus 0.27, so we're at 0.06, minus 0.02, we're at 0.04, and then minus 0.04. Sorry, we're back at 1 here. Sorry, I said that wrong. But if you add that up, equals to 1, you can see that there. So when you add this row up, we'll get 16,206 as that row sum. Now, notice how much larger this is, the r to the 32nd power matrix. Look at how much larger the entries are than those in the R matrix here. And therefore, the row sums are also much larger. So the next step is to normalize the row sums in such a way that the largest value in each vector will be set to 1 in order to make them comparable, that is m1 and m32, with one another. So this is done by dividing each vector by its own maximum value to create comparable k vectors. So we can see that the maximum value in m1 is 1.1 and the maximum value in m32 is 32,123. So I've set it up over here. This is our formula. K sub 1 is going to be m sub 1 divided by the maximum value of m sub 1. So it's going to equal m1 divided by, and I'm just going to do 1.1. And those are our values. Same thing over here to get k32, you do m32 divided by 32,123. And those are the values that we get. Now these values that we just calculated, the k sub 1 and k sub 32, k sub I vectors are referred to as trial eigenvectors. And up to an optimum point, the larger the power of the R matrix, the more precisely accurate will be the corresponding trial eigenvector. So basically what you do is we can go beyond r to the 32nd. And we go r to the 32nd and then to the 64th power, to the 128th, to the 256. And you keep going until you notice that these trial eigenvectors remain the same. So as soon as you get two k vectors, two trial eigenvectors that are the same, in this case it's actually going to be K128 and K256. So using R to the 128th power and R to the 256th power, when we derive the trial eigenvectors from them, they are identical. Well, precisely identical to one another we're going to use 5 decimal places. So we would therefore say that this is the optimal power for our correlation matrix, the power at which this iterative process converges. So that would be K to the 256 as I've denoted here. And I'm going ahead and put the values in here for you. You get the process of what we did over here. So you continue to do that until we get to 256. So the values that we actually get are 0.49343, 0.38207, and then 1. Then we have negative 0.88484, and lastly 0.08017. So this is a trial eigenvector, but it's the optimal power, the trial eigenvector from the optimal power of the correlation matrix. Once again, so you probably figured out, but the reason why they call them trial eigenvectors is we're trying them over and over and over again until we get two that are identical. This is actually identical to K sub 128. So because we find that this is identical, we use this one, the first identical one. So this final vector can now be normalized to 1, as we explained in chapter 3 under normalization. So it can be normalized to 1 to become the true eigenvector K of the correlation matrix R. So what we'll need is the sum of squares of this, and there's a simple way to do that in Excel. You just hit equals SUMSQ for sum of squares, and we're going to highlight this matrix or this vector, and we get 2.179. Now we'll use this to normalize the vector to 1. So I denote that just by K here. So K is going to be equal to K sub 256 divided by the square root of the sum of squares, which is 2.179. And these are the values we get: 0.334, 0.259, 0.677, negative 0.599, and 0.054. So does anything about this that we just calculated, does it look familiar at all? It should, because if we go back here, it's the exact same thing that we got over here. It's the K that we calculated from the loadings reported in the Locurto et al. Paper from this R correlation matrix. So going back, we did a lot today. We did a lot with this. The process is somewhat tedious, especially when we're squaring it. It makes it a lot more helpful to do it in Excel when we can successfully square it pretty quickly. But it is quite tedious, but it is quite simple conceptually. The eigenvector, so this vector, is nothing more than the vector of row sums of the optimal power of the R matrix. So I'll say that again. The eigenvector is nothing more than the vector of row sums of the optimal power of the R matrix. The usual form of this vector, K, is normalized to 1. Okay. So let me just quickly review once again what we did. We have a correlation matrix. This is a matrix that we got, in this case, from looking at the performance of 47 mice on 5 cognitive tasks. And then we did correlations on each of the tasks and came up with this matrix. We then got the row sums of these matrices, or of this matrix, here, denoted by m sub 1. We also did successive squaring up until, well, we demonstrated on here up until the 32nd power, but you can continue, for example, like to the 256th power or higher if you want. And we got the row sums of those. And then we normalized all those vectors to get trial eigenvectors. Then we looked for the optimal power, which we found to be 256, and took that trial eigenvector. And we normalized it to 1, so we divided it by the square root of its sum of squares. In doing so, gave us the true eigenvector k of the correlation matrix R. And there you go. That's a little bit more about factor loadings for today. Note that the method of successive squaring that we did is only one of many methods for finding eigenvalues and the corresponding eigenvectors. But we did it, and it's demonstrated in the book, not because of its computational efficiency, but because it is pedagogically accessible and can be summarized in one reasonable simple sentence. It is also good to note that it is not the algorithm used by stats packages such as SAS, SPSS, and Stata. And so it's just a different method that's good to use, or that's a tool there at your fingertips. But there you go. I hope you enjoyed the video. You have a great day.